Great. Well, it's time now. On Monday, we spent some time just reviewing over everything we had done prior to this point, but now we get to move on to new and more interesting subject. I mean, all the derivative stuff is still interesting, but now we get to go on to the second half of calculus, which is integral calculus. Before we get to that point, I'm going to take a quick stop back at chapter 3 to talk about this idea of something called a differential, right? So, do you remember when we talked about this on Monday? That we have this notion of, delta y over delta x is our slope, right? And using the four-step process, we could write this as, we found that this would be f of x plus delta x minus f of x over delta x. And then we could take the limit of that. So if we took the limit of, as delta x approaches 0, of delta y over delta x, we get dy over dx, right? But there is still an idea that we could kind of separate the delta y and the delta x here. So I could, because we had just delta y by itself, right, is this top portion, and then we divide it like a delta x. So they're kind of separate from each other, but we can put them on top. But when it came to this dy over dx, they were always sort of attached together, right? Like we always, sometimes we had d over dx of x squared, right? So that would be 2x in that case. But this was always just like one notation kind of attached itself together. But this can actually be split up similarly to the delta y over delta x. Like this is also a quotient, right? So in the case over here, for example, right, if dy, so dy over dx in this case is equal to 2x, right? I can also write this as dy equals 2x times dx, okay? And what this is called, what we call this thing in general, so let's say if I have a function, right? So I let y equal f of x, and I take the derivative of that, so I get dy over dx equals f prime of x, and I multiply that dx over. Get dy is going to be equal to f prime of x dx, and this thing, this is called the differential. Okay, that's what we named that. So dy is, which is equal to f prime of x times dx, is the differential, right? Now this isn't just some sort of funny symbol like trickery here, some sort of magic we're doing. It's there's a geometric idea to it, which is kind of goes with this picture I have drawn over here. If we can see, so let's say that this graph is, so this is our f of x, right? At this point down here, I've drawn a tangent line to this particular point that goes down, just kind of stretches along it, but only touching the graph at this one point, right? Now let's say I pick another point on the curve, which is here, right? Which then the corresponding point on the line will be about at this point, okay? In each case, the distance between those two, which is our delta x typically, or what we saw as our delta x, that's the same as our dx, right? So so this length here, right, is the distance between one x point and another x point, right? But the y part is where things start to change. Because delta y is what you would think it's just the distance between the y's, right? So just between this point and this point is delta y, but dy is actually not the distance between the 2 points, but the distance between the point where the tangent line hits and the corresponding point on the tangent line, essentially, right? So dy only goes up as far as the tangent line, whereas delta y extends up to the curve, right? So that's sort of the difference. Delta y is measuring your distance in y between the curve itself, and dy is measuring the distance between the curve at this point and its tangent line at at that same point. Okay, and this is useful because especially as we start to get smaller, right? So let's say I move my dx over here instead of the delta x distance. Dy would be here and delta y would go up to here. They're a lot closer. So it would be a better like guess, like they're closer in value, right? But in general, this idea is actually like having this notion of a differential is very helpful because sometimes it's quicker, like it's to have an approximate of something. It's a lot easier to be able to obtain this dy distance and give a good approximate distance rather than figuring out what that exact delta y is. And we'll see that with a couple examples that we'll do. So, any questions so far on this? Is this kind of making sense a little bit? Well, as I said, we'll practice some examples, and as you see the applications, hopefully it'll start to be like, oh yeah, I see where that comes in. So let's see. The first example, I'm going to erase this board that we're going to do is just to do a little bit of computation to kind of see the difference between them, right? So, well, actually, they use the same term I had. We're going to let y equal x squared, and I'm going to compute. I want to compute delta y and dy, given that and it says that x is equal to 2 and delta x, which is equal to dx, they're the same distance. The y is the part that changes, is equal to 0.01. Good. So I just want to be able to compute delta y and dy, right? Now, if we go back again, kind of look at how we built the 4-step process, we'll remember. So I'm going to write for FST here to try to remember. We saw in the second step that delta y is the same thing as f of x plus delta x minus f of x, right? So we can use this to calculate delta y, right? Because in this case, our f is x squared. So we'll go ahead and kind of plug in x squared first before we plug in any numbers. I'm going to do x plus delta x squared minus x squared, which I think I actually did this example on Monday potentially, but anyway, we get x squared plus 2x delta x plus delta x squared minus x squared. And so we're going to get simply 2x delta x plus delta x squared, right? So this is my delta y, okay? This is kind of the difference between f at this value and f at the other value, f at x plus delta x and f at just x, the initial point essentially. So plugging in now, we'll do that over here maybe. We are going to get that delta y equals, now so we're going to get 2 times x, which we're given that x in this case is 2, times delta x, which we're given in this case is 0.01, plus delta x squared, which is 0.01. Okay, good. So this is how we compute delta y. That just comes from the formula we had up there. And we plug in our numbers. And so we're going to get 4. So we get 2 times 2 is 4. 4 times 0.01 is 0.04 plus, and then what's 0.01 squared? Let's see. Move it over a couple more decimal places. So we'll get 0.0001. So in this case, delta y, this is delta y, right? So if your delta x is small, is that 0.01, then the distance between x at 2 and x at x plus delta x, which in this case is 2.01, is this much. Okay, so when the difference between those x's is pretty minimal in the scheme of. Okay. Now I would say that dy is actually a little bit easier, a little bit faster to calculate, because, right? I erased this. What did I say dy was equal to?
2.01.
Well, I haven't been given dy. I defined it, right? What's the formula? If this is the differential, right? Add it up here. Yeah. Good. F prime of x dx. Good. So notice that these are actually pretty similar, because if maybe I'll write this as an aside, right? If we have, so delta y is f of x plus delta x minus f of x. And normally I'd have over delta x, but we're not worried about that delta x part, right? And so that kind of gets canceled out. Versus with the dy, we have f prime of x is dx, right? So you can see if I took basically in a way, if I took the limit of this thing, I would get this equation. But because of that kind of limiting factor, it changes the value. So f in this case is x squared, right? So what is f prime going to be? Good. Awesome. So dy is equal to 2x dx, right? So I just plug in, right? So x again is 2, and dx is given to me as 0.01. And so this is simply going to be 2 times 2 is 4, 4 times 0.01 is 0.2. Good. So they're pretty close, right? But the significant portion is the fact that 0.0001 is still there, right? Which seems minimal, but that's kind of the point, right? This is a lot faster to calculate, and it's a pretty good estimate, right? We can say the distance between the values is approximately this much. I think that's the end of their calculations for that question. So again, I'll restate it. We'll see, like dy is a good, for small values of dx is a good approximation of delta y, right? So if we're dealing with small changes, instead of computing this, we can opt to use the derivative and check that instead. So cool. Okay. Now we're going to take this and you do some practical examples with it. So we have, so this is example 2 in the book. And it says that we have a resistance that's varying with respect to temperature of a circuit. So we have that resistance is equal to, let's see, 3.5 plus 0.002 squared, and that's in terms of ohm. So that's just the units of the resistor. And then we're given that T is measured to be 100 degrees Celsius with a possible error of plus or minus 1 degree Celsius. Okay, so again, someone measures the temperature to be able to use for the resistor, and they measure it to be 100, but there's a possibility that there's an error of about above 1, below 1 degree of 100. So our goal is in this question is to figure out what is the maximum possible error in the resistance due to this error in the temperature. Okay, because obviously, like, we could just plug in 100 and say that's what the resistance is, but we want to have an understanding of how much that 1 degree will affect the resistance. Right. So to find this approximate maximum error, again, it says approximate, we want to use the differential. Because that's going to make our lives a lot easier, right? It's going to be delta R, but so we don't have to work with that. We're just going to approximate using dr, right? So the first thing we need to know is, well, what's the derivative of R, right? So what is dr over dt going to be in this case? So that's all right. So what's the derivative of 35? It's 0. It just goes to 0. Good. Okay. Now I just have a number times t squared. What's the derivative of t squared? Yeah, so the 2 just multiplies down with the decimal and then you just have t left, right? So it's just going to be 0.004 t, just like that. Okay, so this is our dr over dt, right? So the differential in this case is simply going to look like R is 0.004 t times dt. Okay, so we're asked to find what the approximate maximum error is in the resistance. So we just use the numbers given, which is 100 and plus or minus 1, which we'll just call 1 in this case, because the plus or minus only affects how high or low we go, or like the direction of it. We want to see kind of the size of the error, right? So to plug in, I just take 0.004 times 100 times t, which is 1. What do I get when I do that? Yeah. 0.4 ohms. Which again, if we wanted to worry about the plus or minus, it would just go on the, there'd be a plus or minus 0.4 ohms there. So what's happening in this case? We see that if there's an error of plus or minus 1 degree with the temperature, and we're measuring 100 degrees Celsius, then the approximate error in the resistance is going to be about 0.4 ohms. Okay, so you should expect there to be kind of a flux of 0.4 ohms, no matter what the resistance value is, due to that one error. Okay, does that make sense? Is it a little bit easier to see once you like kind of line it? This is really a lot more about application, about kind of applying it. It's something that may seem a bit odd just by itself, so it's better to put it with something to kind of justify it. Okay. The question also asked for, so what we just found, this is the approximate maximum error. But we can also find something called the approximate relative error. Okay. So, and the way we get this is basically when we say relative, we're wanting to take the value that or this value that we got for the maximum error and kind of compare it to the resistance value at that point, right? Because seeing 0.4, we might say, oh, well, that's pretty small, but what if the resistance is like 0.8? Well, that's not very helpful, right? So we need to see what the actual resistance value is at this point, right? So let's calculate that first. So we want to find the resistance at t equals 100. So I just take 100, plug it in. Sure, it is 3.5. Okay, good. Does someone want to calculate this for me real quick. So if I take 100 squared, I'm gonna get, let's see, 110,000, and then 10,000 times 0.02. That's gonna move it over 4 decimal places, right? So 1, 2, 4. So we get, so this is gonna be 3.5 plus 2.0. So 5.5, is that, get that, I think that's probably. Oh, no, I really did it wrong. Okay, good. Did I write down that? Okay, is it 20? I might have, oh, yeah, because I just didn't, I only went to that point. Yeah, so sorry. That should be 20. So it's 23.5. Apologies. I did 4, but I said 4, but I did 3. That makes sense. Okay, so 23.5 ohms is the actual value, right? So to find our relative error, all I need to do is take the dr value that I found and divide it by the r I got at that point to see how the error compares to the actual value, right? So we're just going to be doing 0.4 over 23.5, which, to save us some time, the book gives us going to be about 0.017 or 1.7%. Okay, so not too bad, but it's still significant, right? Because the temperature, it was 1 plus or minus 1 degree off, and so that's only 1% of its amount, right? But that 1% error on the temperature caused a 1.7% error on the resistance, which still not much bigger, but it's still bigger, right? Like the little change in that caused a bigger change in this, right? So it's something worth considering. It's something worth thinking about. Okay, good. Any questions, comments, or concerns on that? Nope. Good. Okay. With that, if there's no other questions, you can feel free to look at example 4. It's a similar idea, where it's essentially just saying you're applying a coat to a certain thickness, and so you want to see how much you actually have to, you would actually have to use approximately given that little section, in according to whatever the radius is. But similar idea to this. Okay, good. Yes.
So you have to multiply the error by that derivative equation every time, or plus or minus 1.
So that's dt, right? Yeah, so this is, remember, the differential, so we had used R and T here, but in general, our differential is dx, right? So that dt we multiply by is sort of the equivalent to the dx here, right? So you have the derivative and then you're multiplying by whatever that little error value is. So yes, you are multiplying by the error value at all times. So you take the derivative, you find the value of the derivative at a given point, and then you multiply by the error.
Okay. And that's the dx as well.
Yeah. So that, so the dx is the error here. In this case, it's dt, but it's just we're using different variables.
Okay.
It's the same process. And then so this gives us the error in the approximate error in dy or dr in this case. Okay. Cool. Okay. Good. So that's 3.6. That was chapter 3 again, so great. But the reason that I waited until now to do that because this notion pops up again for what we're about to get into, which is chapter 4. Okay. Chapter 4. So I want to remind everybody that right, we're done learning about derivatives. We have all the derivative rules in our with us now. There's a couple other little derivatives you can learn how to do, but there's always some sort of formula that uses things that we already know. So you know how to do all the derivatives, right? But we don't want to just stop at knowing how to do derivatives, right? Because we could keep going down as much as we want, but sometimes it might be more useful instead of going down, basically like taking the derivative, leveling, moving down a level in each case, that we wanted to go the opposite direction with antiderivatives. Yeah. Isn't that exciting? Okay, so antiderivatives. What is this? How do we do this? How do we think about this? Okay, so the book starts with an appeal to actually talking about acceleration and velocity, and so I'll start that same way, right? So there was a problem with the quiz, right, where you had a position, right? And when you took the derivative, you get the velocity, and when you take the derivative, that you get the acceleration, right? But what if we're in a situation where I know the acceleration, so let's just say here's metric system, 9.8 meters per second squared. So this is gravity. Let's say I know gravity and I want to figure out the position of a particle from knowing this information, right? So I don't know the position, I want to get acceleration. I know the acceleration, I want to get to a position, or even velocity, right? Well, that's going to require us to go backwards, right? In this case, getting to velocity is pretty simple from here, because all that's happening, right, is with the acceleration, right? I'm going to move, after I go so much time, the acceleration is going to apply more, or it's going to apply less, right? So velocity in this case is just going to be 9.8 times time, right? Which makes sense. If I take the derivative of 9.8t, what do I get? I get 9.8, right? So that's the acceleration, okay? So this is my velocity, right? Now, the thing we have to worry about here, though, that we didn't have to worry about with derivatives, is the fact that this is not unique. What do I mean by that? So let's go back to our x squared example, right? If I take the derivative of this, what's the derivative? 2x. Good. So if I attempt to go backwards, a lot of us might just say, oh, well, it's x squared. What if it was x squared plus 1? Isn't that its derivative? What about x squared plus 2? Isn't that its derivative? What about x squared plus pi, or square root of 2, or any number on there? I'll just put x squared plus c. All of these have the same derivative, which is 2, right? So whenever we're talking about antiderivatives, that's something important that we have to keep in mind, is the fact that if I'm going backwards, I can't just say, oh, I just left the t on, I'm good. I have to consider the possibility that there's some extra constant involved, right? That there's a plus c, some number that disappeared going to this step, but was originally present in this step, right? So velocity in this case is represented by 9.8 t plus c, right? And then I could go from here to be able to get what the position is, right? Which I will admit that doing antiderivatives can be a little bit more challenging at times than doing derivatives, because there's a bit more to consider, right? Just as a quick example, right? Whenever you're doing chain rule, right? You basically were taking something that was allowed to kind of like just come out, right? It kind of sat on the side. But now with antiderivatives, sometimes you have to work not to just push something to the outside. You have to figure out how it can pull itself back in, right? So that leads to a bunch of interesting possibilities, which we'll get to how to address those in this class and more in depth with other examples in Cal 2. But we have still some simple examples, right? So let's go to, let's just start with, again, let's go with x squared, right? So how would I take the antiderivative of this thing, right? Which first, I'll use the book's notation. call that, this is f of x, right? And so I want to go up a level. I want to find its antiderivative, which I will label as, well, big F of x. So instead of f prime, now we got big F, right? So here's a question. What thing would I have to take the derivative of to give me an x squared term? Well, just more x cubed for now, right? We just need, it doesn't matter what the constant is in front. I need an x cubed to get to an x squared, right? Because the derivative of x cubed ultimately is to get an x squared because I go down the road, right? So f of x in this case has to be some sort of x cubed, right? But if we take the derivative of f of x right now, right, this should be whatever f of x is. But the derivative of this guy is 3x squared, which is not the same thing as x squared, right? So, as Blaine already said, the way that I fix this is that, similar to when you take the derivative and a number comes in front, you have to introduce another constant with this. And in this case, it's going to be x cubed divided by 3, right? Because that'll cancel out this 3 and give us x squared. So the antiderivative of x squared is x cubed over 3. So let's get more general. If f of x equals x to the n power, then big F of x, which is its antiderivative. Oh, actually, I should mention, should be a plus c there, right? Because again, we don't know. There could be, like, it could be any constant, right? So big F of x is x to the n plus 1. And notice these powers match. So similar here, we're going to get n plus 1 on the bottom, and then plus constant. Because again, if we took the derivative of that constant, it would be 0, so it wouldn't check. But the derivative of this thing is x to the n. Okay, so kind of reverse, besides the differential, first formula for this section. Okay. Yeah.
So C can be basically.
That's something we'll get into in a later section. For now, you just assume that you just leave it general. Because we won't know unless there's other conditions given for you to say. All we care about is basically how to take an antiderivative at this point. So you always need that. So that actually brings up a good point. Whenever you're finding antiderivatives, if it's not some sort of special situation where the c won't be there, which we'll get into later, there better be a plus c when you do it, right? Because if you don't put a plus c, it's wrong. Technically. So that's how in the past in my classes I've gotten points up because I've got to put a plus c at the end. So always remember to put the plus c. It's very important. Okay. So with that, we have a couple more formulas. I think that's really all. So they do just do some examples. If f of x to k x to the n. So now we just have some number on the front. Then big F of x to k times x to the n plus 1 over n. Okay, so literally how you think like just how derivatives are, that constant that's on the front of the term just comes along. It doesn't affect it. It just kind of phases through. Finally, if f of x k, then big F of x is simply k times x. Okay, so if you just have a constant, then you attach an x up to it as its antiderivative. Okay. Plus c. Good. Thank you. See, I'm telling you, it's easy. Gotta make sure it's there. I have to write it like this for now just because we're introducing the notation for this later, but for now it's just a concept. So we're doing it. Right. So let's run through a couple of just quick examples of these. So I'll box that, we do need that are all necessary. Okay, so let's say we have, let's do. What is, okay, so we were given that f of x is 3x squared plus 2x plus 1, okay? And I want to figure out what is f of x, okay? So let's kind of walk through this together. So how do I find the antiderivative of 3x squared? Right, what's going to happen to this 3? Yeah, it just moves to the next step. It doesn't change. So we have 3. Okay. How do I do? What is the antiderivative of x squared going to be? So right, so we have x to the 2 plus 1, which is x3 over 2 plus 1, which is 3. Good. So there's that term. Plus 2. Right, the 2 again will carry. What is the antiderivative of x? Good. So we want to recognize it's 2x to the first power, right? So we're going to get 2 times x to the second power all over 2. Again, coming from the same formula, okay? And then what is the antiderivative of 1? 1x. Good. Okay, awesome. So I did set this up specifically, so all these will cancel, right? But so we get, so the 3's cancel, the 2's cancel, and so f of x ends up being x cubed plus x. Okay, so that is the antiderivative plus c. Good. Get the test, you guys. Yeah. Let's see. Okay, good. So plus c. Awesome. Any questions so far on this? Okay, let's do another example. And then I might what time of day? Okay. Okay, yeah. Let's do one that isn't just our normal powers. Let's take f of x is square root of x plus. So we'll move it. So we're gonna have, maybe we'll do f of x would be 3 times the square root of x plus 2 over x squared. Okay, good. So let's see. What should the first steps be here? What are some ideas?
Get rid of the square root.
Okay, get rid of the square root. What do you do?
1/2.
Good. So we won't get rid of it necessarily, but we'll rewrite it as x to the 1/2, right? So it's still there, just sort of a form that's a bit more palpable to us. Okay. How should I rewrite this guy? 2 times x to the negative second power. And then we have our, how should I rewrite plus 1? I should. Right. Okay. So let's find f of x. How do I do it? So now 3. Okay. 1/2 plus 1. Good. Divided, well, not divided by 3, right? It's n plus 1. So it's 1/2. It's also 1/2 plus 1. Basically, whatever the power is here, the denominator should be the same. Okay, so we'll fix that in a bit. Okay, this one.
2 times x to the negative
Good.
over a negative 1.
Good. And then plus, yeah, just x. Because it's going to be 1 times x, which is just x. Okay, good. Let's see. Yeah, good. Let's see. Yeah. I knew it that time. I just couldn't see. Okay, so now we can do a little bit of simplification here. So we're going to have 3 times. So we have 1/2 plus 1. So we have x to the 3/2 over 3/2 plus, well, actually, this is divided by -1. So I'll just say -2 times x to the negative first power plus x plus c. Okay. And then how could I do? So what do I want to do with this 3/2? The denominator. Leave it and walk away. Well, that's fine. I don't generally like fractions in my fractions unless I specifically say you can leave them. This is right. You would end up just, it would flip, so you'd be multiplied by 2/3 instead. Right. So instead of dividing by 3/2, you multiply by 2/3. Minus 2 over x plus x plus c, which then the 3 gets out here. So 2x over 3/2 minus 2 over x. Good. That makes sense? Everybody following on that? Definitely a section you just want to have your formulas and practice. Yes. Practice. It'll help you. It'll help you to learn it. Okay. There's only so far I can go. Good. Okay. So that is antiderivatives. Okay. So we still have 10 minutes left, so I'd like to go ahead and hop into, so the baby 4.2 is now a 4.2. Okay, so what's the point? Why would I use these? Well, we'll get to that. And probably, hopefully by Monday, we can at least introduce the concept. But for now, I need to introduce. Let me erase, get some space. Okay. So this section of the book is called the area problem. Now, it's called the area problem because if I ask you to find the area of a triangle, right? It just even just a simple right triangle like this, I'm gonna give you the base and height. What's the area of that triangle? Right. What's the area of a circle? Pi r squared. Yeah, not 2 pi r is the circumference. What's the area of a square? Yeah, well, a rectangle is length times width. A square is just where the sides is squared because they have the same side, right? So, and a lot of times we can construct shapes to represent our areas so that we can just find it from adding things together. But what happens if I get something like this and I want to find the area underneath it? Wow. Now we have a problem. Well, yes, but also even with that, the computer has a process that we need to learn. We know what it does. So yeah, everything in this class you can technically try to program the computer to do it, but we want to learn why the computer does what it does, right? So how do we go about this? Well, we're going to basically how we're going to break this down is again, just like I was talking about, like, so for example, if I had like, this sort of house shape or something, I could break it down into different pieces and then add up the area of that. So the idea here is maybe to again take this thing and kind of break it up into pieces, right? So if I split it up into however many, 1, 2, 3, 4, 5, 6, 7, 8, 9, and about 10 pieces or whatever. And I would take each area, a little area, which I'll just call little a, right? And then just kind of add them along to give a good estimate, right? And each of those I would have to break down and look at and take apart. Now, sometimes I don't want to write down every term. So we're going to introduce a new notation here, which is called sigma notation. Which is where, so each of these terms, I put a little subscript on it. So if this is A1, A2, A3, A4. So we kind of put it in this little sigma notation, which will have each of them labeled. We'll know what each of them are. We'll call them something. And this will go from a number, we'll start from 1 generally and go up to however far you're doing, right? So in this case, it's 10, but sometimes it may be 100 or 1,000 or some sort, right? And so when we're breaking up into little pieces, it's useful to have something like this. And so maybe we can get a general idea of what each piece looks like and then just write it neatly and add it together, right? So, just as a few quick examples, right? Let's say that each AI, right, was equal to I squared, right? Then this, I would write the notation out as I squared, and then in each case I would plug in I, right? So it would look like 1 squared plus 2 squared plus 3 squared plus all the way up to n squared, right? So I would just plug in each I up until I get to n, and that would be my sum, right? Or if I was doing, like it also has 1 over I, right? Then it would be the same story, 1 over 1 plus 1 over 2 plus all the way to 1. Right? So that's what that sigma notation is doing. That makes it really useful to work with them. Because again, as I said, you could try to break this up into just look at each of them differently, and so they're not related to each other, but that's going to take a while. So if we can have a general process of getting them, we want to kind of put it into a mechanism like this to find value. Okay, so what sort of use does this have for us? Well, again, someone already said it. You could find a lot of shapes to put inside this curve here, but the easiest one would just be to do a whole bunch of rectangles, right? Put a rectangle here, rectangle here, rectangle here, maybe a rectangle here, here, and out of the area of a bunch of rectangles, right? If you wanted to have smaller rectangles, you could probably get even a little bit better, right? So we're just taking a bunch of rectangles and adding them up, right? And each time you want to have, so it looks like it has a couple examples of like doing a few weird subdivisions, right? Like like it might have these ones be small, but it might have this one be big, and this one be small. Which there could be a pattern to this, but it makes it a little difficult to express likewise. But the idea here is that if I have some sort of pattern, right, then I can find an easy way to subdivide, right? That will make it so this addition, this sum, is going to be as simple as possible, right? Now, notice in each case, right, how I've drawn each of the rectangles, that each of them is going to hit the curve at some point, right? And that point, well, again, is a point on the curve. So there's, for some x value here, we'll call xi, right? This value here is f of xi, right? Now, since that represents our y direction, right? That's essentially what the length of that rectangle is, right? And then in each case, right, I might have some sort of, I have some sort of length down here, right? Which is just some given distance between the axes, right? So each rectangle, right? I take just some xi, right? Some value along that curve, and that'll give me the height of my rectangle. And then I might designate something for each length. Maybe I'll call that delta x, right? So it may change accordingly, but that's the length of each, that's the distance between each of the x values, right? So now I have this neat little formula, right? That if I want to take it and turn it into some notation, right? This is just a bunch of rectangles being added up, right? But it uses the function, right? And it uses our neat little subdivisions, however we just define those to be, right? And so ideally, right, if I choose to use a higher n value, then I should be using more rectangles, which should better approximate what's happening underneath the curve. Right? So, but we don't want to keep testing, right? Testing all these different ends and keep getting higher and get a guess, right? We want to see what happens if I make those rectangles as small as humanly possible. I want to take those rectangles and I basically want to like them to be basically skinny, right? And what that means is that, right, if I make this so I have, as I go towards infinity, essentially, if I keep adding rectangles in so that they're infinitely small, right? I should ideally get a better approximation, right? So why don't I take this sum and take the limit of it, right? So notice again that I define each of these xi's according to and the n according to how I want to subdivide, right? So if I make n large enough so that I cover all that space, right, neatly, and I take the limit of it, ideally it should give me that area underneath the curve. And this is what we call, and this formula gives us your area under. Okay, so I'll go ahead and stop there for today. And we'll spend the beginning of Monday working with how to apply this and work with it. Yeah, but that's the